Use cases are used within UML to capture the usage requirements for a system. Use case diagrams are extremely useful for communicating with stakeholders and other non-developers. The textual representations of use cases, however, are invaluable to both developers and stakeholders, for they describe what the actual user and system will do in response to typical stimuli. In this video, we are going to show you how use cases can be used to drive the testing process, allowing a tester to develop test cases directly from the user's usage of the system and essentially from the documentation of the use cases. So our goals or objectives are to explain the purpose for the use case diagram, given a use case, be able to construct an activity diagram, which again is a UML diagram, showing the flow through the use case, and then given an activity diagram, construct a set of test cases to fully exercise the use case. This is a picture of a car security system called the ThugBug. The ThugBug was a vehicle security system common in the 1980s. It essentially had two features. The first feature was the requirement to enter a 4-digit key code prior to starting the car. Without entering the proper key code, the car would not start. Additionally, the system featured a vehicular hood lock. The hood lock prevented thieves from opening the hood unless they entered the same 4-digit key code. This helped to prevent the theft of devices such as batteries or other things from underneath the hood. The ThugBug used a standard numeric keypad, such as the keypad shown on the screen right now. To start the car, the user placed the key in the accessory mode, powering the security device, entered the 4-digit code into the keypad, for example, 1596, and then cranked the vehicle. If the key code was incorrect, the security system prevented the car from starting. It was novel and ingenious, but also pretty simple. The system also required the entry of a key code to open the hood. To open the hood, the user turned the car again into the accessory position and entered the 4-digit code, 1596 for example, and then pressed and held the 0 button for 5 seconds, after which the hood would unlock. Again, it was simple, ingenious, and prevented what was then a common problem, the theft of vehicle batteries. In this video, we are going to use the ThugBug system as an example to describe how one can use use cases to develop tests for a given system. By definition, a use case represents a named capability of a structural entity within a system. Essentially, that's kind of a big meaning or big word for it's an explanation of how someone would use the system or some capability of the system to do something. A use case diagram is a diagram showing the use cases and their relationship with the actors, where the actors are essentially the external entities that interact with the system that we are building. Let's take a look at an example of this. Here we see a use case diagram for a banking system. Essentially, we have the ATM user. The user can authenticate, deposit money, withdraw money, or view account balances. These use cases interact with the bank account management system. Typically what we will have is this over here on the left is our user. So the ATM user would like to authenticate. There are certain steps that will go on within this use case right here in order for this ATM user to authenticate. Once the user has authenticated, if they would like to deposit money, they will go through another set of steps, indicating how much they would like to deposit, which account they would like to deposit into, so on and so forth. These, again, will be interacting with this bank account management system that's over under the right. Withdrawing money, same type of scenario, where the user will enter information about what their account is, how much they'd like to withdraw, all the various steps that you need to complete in order to withdraw money. The view account balance, again, is a similar type of thing. Each of these things that is listed in here basically are essentially the system actions or essentially the use cases, how we would use the system. These little stick figures that we see out here on the left and right, these are called the actors. So the actors essentially are the external entities which interact with the system. The system under construction is represented by this boundary. So this boundary essentially defines the scope of what we are building as part of our system. In our particular scenario here for this drive-up ATM system, we are not actually building the bank account management systems. These pieces that are over here on the right, they already exist. But we are building the things that are necessary to do the actions that are inside of the scope of this system. So let's take a look at our example, the ThugBug. The ThugBug essentially has a driver, and we've had this system here, the security system called the ThugBug, which is added into our vehicle. There are some interactions with existing vehicle electronics in order to complete some of the use cases, but not all the use cases have interactions with them. The driver may start the vehicle, the driver may open the hood, or the driver may change the key code. Notice that these two use cases that we have here do not interact with the vehicle electronics. They are completely independent of the external vehicle electronics. The scope of the security system is shown essentially by, again, this boundary box right here. In this particular case, the main actor is essentially the driver that's over here on the left, because the driver can do each of these three use cases. Now graphically, this use case diagram is great as essentially a table of contents for what the system can do, but it doesn't really help us much to explain the specifics of what goes on underneath the hood of each one of these use cases. Because we need some additional information in what we have in that use case diagram, we commonly will elaborate on our use cases. So essentially, we will document them. Typically, unlike a lot of other things in UML and with design and code implementation, this tends to be something that is in a textual form. So it's something that can be read by a common user. The elaboration is going to include details and possibly some alternative operations that can occur. Things that may happen differently as the use case actually goes through. Let's take a look at one of these described. So on the screen right now, we're looking at a use case elaboration for the open hood use case scenario. So in summary, in this use case, the driver of the vehicle successfully opens the hood of the vehicle. Pretty succinct summary. The actor that is involved in this happens to be the driver. So all of this up above is essentially very, very high level information that's intuitively obvious to some extent from the use case name and the use case diagram. What we have below now are some of the other things that help us to actually make heads or tails out of this use case. So for example, a precondition in this scenario. The key must be in the ignition. If the key is not in the ignition, this use case is not going to be active. The post condition, essentially what happens after the use case is done, is that for the most part, the hood of the vehicle will be opened. The flow through this essentially consists of these three steps. So the user places the key into the accessory position. So just the key being in the ignition does not mean it's in the accessory position or the correct mode to perform this operation. The key has to be in the accessory position. Once the user has placed the key in the accessory position, the car activates the vehicle electronics. So typically if you wanted to listen to the radio in your vehicle without having the vehicle turned on, you would have the key in the accessory position, allowing the radio to be listened to. In this scenario, to open the hood, the key needs to be in this same accessory position. Once the key is in the accessory position, the user enters a 4-digit security code on the keypad. So, for example, 1593, for example. The system will then verify that that code is correct, and if it is correct, the user can press and hold the 0 button for 5 seconds to unlock the hood, allowing the hood to swing open. This bottom section describes some alternatives that can occur, or alternative flows. For example, if the key code that is entered is incorrect, the hood's going to remain locked. Based upon the way the system is designed, the user may try re-entering the security code one more time. That will take the user then back to this step 2. If they enter it successfully, obviously they can press and hold the 0 button for 5 seconds to unlock the hood. However, if the code is entered incorrect for a second time, the hood is again going to remain locked, and the user must cycle the ignition, going all the way back up, exiting out, and starting over at the top of the use case again. So those are the two alternative flows out of this step 2. From step 3, here, if for some reason the user does not hold the button for a full 5 seconds, in our case, the use case is aborted. The hood remains locked. This is a scenario where the user decided they didn't really want to open the hood, or they just didn't want to wait 5 seconds. Again, the key thing about it is if this alternative occurs, the use case is aborted, and we do not get to this normal post condition in this scenario. So this essentially is, again, the elaboration. And you'll notice again that this is predominantly text describing what happens inside of the use case. The textual descriptions we looked at previously do a wonderful job of describing the behavior of the system. What we would like to do is essentially show this information in a visual format. A visual format allows us to better see what is going on inside of our system. So we're going to do this through the usage of what's called an activity diagram. This again is a UML diagram that allows us to capture dynamic behavior of the system by essentially creating a flowchart showing how we go through the use case. Now in our flowchart here, we're going to really have two kinds of nodes. We're going to have action states where essentially things get done, and these are derived essentially from our use case descriptions. We also have essentially branches that are derived from the alternate flows, where essentially we're going to go down to an alternate flow because something happened that causes that alternate flow to become active. The flow between the steps then become our edges. And so from this, we essentially again have a flowchart showing how we would walk through the given activity. Let's take a look at this for one of the examples in our ThugBug system. So on the screen right now, we are looking at an activity diagram for essentially the open hood use case. So we see that this begins by the key being placed in the accessory position, which causes the vehicle accessory mode to be activated, and then the user enters the 4-digit code. Now, if the code is verified correctly, and then the user holds the button for 5 seconds, we go over here, unlock the hood, and essentially we are done. If for some reason the 4-digit code is incorrect, we're going to take this path going over here. If it's incorrect only for the first time, we will come back. Otherwise, if it's incorrect for the second time, we will essentially abort the use case, taking this path down here. If the user has entered it incorrectly one time, then the code is verified, they hold the button, but they don't hold it for a full 5 seconds, we go down here and again abort the use case. So we can see graphically that this is really showing the flow through a flowchart structure through this given use case. Now from a testing standpoint, this use case diagram that we saw previously doesn't really help us a whole lot. Basically, the most that we could accomplish from this is essentially seeing if we have node coverage, which essentially node coverage in this scenario would mean I've hit each one of the use cases exactly once. Basically, if we're talking about code coverage, that's the equivalent of testing with method coverage, which, as we know, is not a very good way for testing code. But if we go from this and take the activity diagram that is generated from the textual description of these use cases, we can then actually generate a graph that's going to give us some useful information for testing. Let's take a look at that. Here we see a graph that is generated from the activity diagram that we looked at previously, and within reason you can see how some of the flows do match together. We have essentially down here at the very bottom 3 essential final nodes where things actually end up finishing up at and wrapping up. Those 3 final states essentially map with these states that I have here, here, and here, like so. So those three states map together. This here is essentially the same loop that I have right over here in terms of going from the user holding a button for 5 seconds, so on and so forth. So we can see that there is a strong relationship between these two diagrams. So covering activity graphs, we have the concept of something called a use case scenario. So a use case scenario essentially is a single path through the use case from the start to the end. It's essentially how we walk through this user activity. We can then use different coverage models on this graph to figure out how to do our testing. So for example, the simplest is going to be node coverage. We may get something more complex that is edge coverage, and then we may get to a more advanced thing called specified path coverage, where we're going to look at the specific paths that we need to take. Let's take a look at this. So if I wanted to have basically node coverage with this system, what I can tell you is from the graph that we have, I'm going to need at least 3 test cases to be created. The reason I can say there are 3 test cases is there are 3 final nodes in this scenario. So one of my test cases is going to go down and do that, where we are essentially taking the happy path the whole way. One of my test cases will do that. The basic difference between that red and that orange path that I have just drawn is in the red path, I press and hold the button for 5 seconds. In the orange path, I don't press and hold it for 5 seconds. The red path, the hood will be unlocked. The orange path, it will not be unlocked. The last path that I have here, I'm going to do it kind of in purple, would be across like this. And again, that path there is a result of me entering an incorrect security code into the system. So I can see with these 3 test cases that I can achieve node coverage. That may not be the best way of testing this system. So the next thing I might want to do is go to edge coverage. Now, edge coverage, I can do this a little bit differently. With edge coverage, I could maybe start by taking a path here where I go over. I'm currently incorrectly entering the key code. I come back. Now I enter it correctly. I hold the button for 5 seconds. I come down here and I finish out with the hood being unlocked. That is one way I can achieve edge coverage. Now, what I have is another scenario here where I maybe enter the information correctly on the first try. I come down, but I don't hold the button for 5 seconds, causing me to go into the state here where I don't open the hood. Last but not least here, I'm going to have to get to this last edge over here. So what I do is I enter it incorrectly. And I go down here. But wait a minute. If we think about it, I can't directly take that path there because I've got to actually be wrong for 2 times. So that's going to cause me to actually loop back and around like so. So those are essentially giving me edge coverage for the system. You'll notice that every one of the edges that's in the graph has a corresponding line that's been drawn over it indicating coverage. Now, specified path coverage, maybe I want to use my specified path coverage as essentially being maybe edge pair coverage. Or maybe what I want to do is have all of the potential outcomes of this system be met in most appropriate fashion. If we remember, based upon the use case, I actually can't take this combination on the first try because I've got to enter my code in correctly 2 times in order to take that path where I go to this path requiring me to restart the system or restart the use case. So let's take a look at what this would be if I was trying to gain essentially the equivalent of edge pair coverage from this. So if I go down here, obviously I can take this straightforward happy path like so, which is good. I can also then take this other path where I come down here and I go off like so. Now what I would like to do is come into a scenario where I do something here. I come over here. I took that edge pair there I'm going to go up and around, come back like this. Now, I need to essentially swing back around here and then go down for one of the scenarios. That takes care of this edge pair between here and here, like so. But last but not least, I'm going to need a fourth scenario here to fully test things, where what's going to happen is I come down here, I go over here, I come down like so, and then it really doesn't matter. I'm going to go to the happy path here. So what those are scenarios that are different is, in one scenario I've got where the user enters the code correctly and essentially opens the hood. Another scenario, the user enters the code correctly but doesn't hold the button long enough, causing the hood not to open. In a third scenario, the user enters the code incorrectly the first time, fat fingers it for example, but yet the second time they enter it correctly, which causes them to take essentially that light blue path. And the fourth scenario that I've got here is essentially the user enters the code incorrectly the first time, they enter it incorrectly the second time, and therefore they get locked out of the system, forcing them to recycle the system. How can I accomplish that testing then? Well, what I have to do is look at the paths that I want to achieve here. So these are the paths from the graphs that I had up previously. And then I figure out what are the initial conditions that must be true in order to exercise them. So I've given an initial condition in each case that the key must be in the ignition and that the key code of this security system has been set to a given value, 1, 2, 3, 4. Why 1, 2, 3, 4? Because it's probably the most common luggage scenario ever. The test steps that we take are then shown in this area right here. So this is what essentially the tester does to the system, either in a manual standpoint or it could be automated. Now, in the case of the ThugBug system, since this was in a vehicle, it probably was manual testing at the time. But if we're building a computer system for this, it could be automated as well. So those are the steps that we go through as we take the paths through the graph. And then last but not least, we get down to the bottom, what we expect to have happen in the end. So we can see that in these two cases here, the hood remains locked. In these two cases, the hood remains unlocked, which essentially matches with what I showed on the previous slide. So at this point, we've looked at how you can construct test cases from use cases. Again, reviewing, you should be able to explain the purpose for the use case diagram. Given a use case, construct an activity diagram showing the flow through the use case. And then given an activity diagram, construct a set of test cases that fully exercise the use case. These test cases essentially will be constructed using some of the concepts of graph theory that have been talked about previously in terms of coverage. That brings this video to a conclusion.